an agent that also do the planning. So maybe not so much on doing only on reflex. So basically, you would want your agent to be able to like perceive the environment and consider do the planning bit, yeah. And you will have all these because it all depends on your performance, how you measure the optimal, yeah, depending on the problem as well. So in the end of the day, you are trying to search the solution, yeah. So it is, I would say, the agent that you are trying to come up with is a problem solving agent, yeah, where you are trying to search for the goal. So just now when we are looking at the piece, you have your actuator and sensor and so on. You realize that you are talking about sensors and the actuators, depending on how your agent will look like. Because sometimes an agent can be a robot, an agent can be simply a computer system, yeah. So whatever it is, it has its actuators and its sensors. So the agent basically has an architecture plus a program, right? So the program will do that question mark, and that architecture is actually basically you have your hardware that you will need to take into account, right? Yeah, so we move to search, because at the end of the day you want to search for the solution. So in a problem you can formulate the problem as a search problem. Okay, so a search problem should consist of a state space. Okay, so the state space is basically telling you the state of which the agent can be. Say for example in here, the small images here, if you look at this, the first one on the left, you have your Pac-Man in the middle, yeah, and your Pac-Man can be in any position. Okay, so the position here, there are three by three kind of plane here. So at every, or you can look at it as a tile, you can have your agent to be in any of these tile, yeah. But it is not only telling you of the location, but you need to also consider, because your goal is also including the eating the white dot. So even the placement of the white dot is considered to be a state, yeah. So if you look at the first one here on the left, in comparison to one, 2, 3, 4, 5, the fifth one, they are both in the middle, but they are completely different state, yeah. Because the first one still has the white dot, and also the position of your agent. Yeah, the first one, the agent is facing on the on the right, and then the on the fifth one, it's facing upwards. Yeah, so all these are different state. So I hope you understand what is a state space is. The spaces at which your agent could be in the environment. Okay. And the environment can have many things as well. Then you will have a successor function, meaning to say the action that your agent can take and at what cost. Okay, what is the cost for it if it were to take that action? Yeah, so this is an example of a successor function. So for example, you start off with this on the left here. Okay, you start off the position of the agent is at the bottom left. So what can he do? He can either go to the east, which is E for east, yeah, which is going to the right, or it can go up to the north, and it's north, yeah. So either to the left, to the right, or to the top here, yeah. So hence the next position that he will be is it's shown after the arrow here. Okay, so we can put the the action is going north with the cost 1, or going east with the cost 1. Okay, so this is just one example. Yeah, this is for this particular problem. Yeah. So in a search problem also, you will have a start state. That's the initial state your agent is. And of course, you will have a goal. You need to know what is the goal. Hence, you should also have a goal test. Yeah, because you need to test whether you have already reached the goal or not, right? So what is the solution to the problem? So the solution is a sequence of these actions. The sequence of this action that you take. Okay, and that is the plan. Okay, which transform the start state. Okay, you have the start state to a goal state. So you have a start state and you have a goal state. So what are the sequences that you take, the sequence of actions that you take in order to reach that goal state? So that whole thing, this sequence of actions, is called the solution. All right. So we can look at such problems as models, because it basically mimics the world, the environment, right? Okay, so because if you remember, what do you have in a search problems? You have all this, your state space. So state space would be your how you perceive the environment. Yeah, and that's how you formulate it in such a way that you move. So you're changing your state by executing the successor function. Yeah, you are changing your state by executing your successor function. All right. So you are mimicking something that is, so that's why it is seen as a model as well, because of, you are actually mimicking the world, your problem, basically. Yeah. Okay, so let's look at an example here. we want to travel in Romania. Okay, so we can start from Arad, that's a city, and the goal is to reach Bucharest. So the Bucharest is down here. Okay. So you notice because you've seen this graph. I would say this is a graph. You can see that there are many cities, right? And obviously you want to reach Bucharest. So, what would be the path to reach to Bucharest, right? So the state space, So your agent is moving, yeah. So your agent is moving, and you want to reach to Bucharest. So what is the state space here? So obviously, the state, because your only goal here is to reach Bucharest. So therefore, the state will change according to the city, right? As you go to the city, then you change. That's your new location, yeah, your new city. So that is your state space. Yes, according to your city. So what is your successor function for this case? So for this case, you are moving. So from Arad, you can move to three cities, right? Timisoara, Sibiu, Ozerin, right? So it's like you're moving city to city. And what do you have here? There's a number there. So that one you can take it as maybe the distance. So if it is the distance and you want to arrive Bucharest in a shorter time, therefore that could be the cost. Yeah, the cost of moving from where you are right now to the next one. Yeah, so therefore your successor function can be the adjacent city with cost, the distance. Yeah, it's basically so the roads that you have from where you are to the next one. Yeah, so that's your successor function. So start state, obviously, that one is given for this particular problem where you are at Arad, and the goal test is basically is the state that where you are right now in Bucharest. Yeah, so that is your goal test. So every time when you move, you will do the goal test, check whether you are you in Bucharest, right? So yeah, so this is an example. So what is the solution? Since we can see here, you can have Arad to Sibiu to Fagaras to Bucharest, right? So that is the shortest, I would say. But obviously, you can see that there are many solutions, right? You can actually have Arad to Timisoara, to Lugoj, to Mehadia, Dobreta, Craiova, Pitești, and then Bucharest. That is again, it's a solution, right? It's a path. However, that is not the optimal one, right? Yeah. And many more. So there are other path that you can follow as you execute your successor function to reach your goal. Yeah. Okay. So what's in a state space? So just now, for this particular example, we say it's cities. Their state space is cities. So for this particular one, you notice that you can go to any of the cities following your successor function, right? So it depends on the problem that you have. Okay. But would you consider everything? So there are actually many states that you can be in, but for you do not need to consider all of them. Yeah. So there's a difference between world state and state space. So state space would be I would say a subset of the world state. Yeah, because the world state will include every last detail of the environment, everything. So that is the world state, of which you will need to consider looking at your goal, whether you want to take all of them. Yeah. So usually you do not take the world state everything. Yeah. You just need to consider only the state space. Okay. A search state keeps only the details needed for planning. Yeah, what you need in order for you to plan to reach to your goal. Yeah, it doesn't have to consider the whole state. Yeah. So just like what we did in here, because we have this a graph, so your world state would be all of them, right? However, for your state space, you would probably just consider looking at, because you are starting with Arad, then you are looking at Timisoara, Sibiu, and Zeren, right? And then from Sibiu, you have to Oradia, to Fagaras, to Rimiku. So you will only consider a few of them, not all of them. Yeah, for example, named Lassi, Vashlu. Why would you want to consider this part, right? Because your goal is here, almost in the middle. So things like that, but you know that they are all states. So they are all of these are your world space. Yeah. But the state space are only a few. Yeah. So maybe you don't quite see that here now because the environment that we have is small. Okay. So yeah, as I mentioned, so the search state keeps only the details needed for your planning. So for a pathing problem like the cities just now, you can have the location as your state. So the city like just now, yeah. And maybe your action is moving north, south, east, and west. Okay, so since we are using this environment, sorry, the Pac-Man environment, yeah. So the Pac-Man environment, if your problem is on your path, yeah, the path that you are taking, so the states would be your location in the environment. Okay. Then your action would be to move north, south, east, or west. Okay. And your successor function would be as you take the action, then you will need to update your location, right? That's your successor function. Then for a goal test is you want to know whether you have reached your location that you want to be as n. Yeah. But if your problem is to eat all the dots, then your state would need to consider these dots, the white dot. Yeah. So not only do you need to know your location, but also your whether you have the white dot or not. Yeah. So that's why it's dot boolean, because it's 1 or 0, right? And again, the action is the same. It can move north, south, east, west. And therefore your successor would be to update your location and possibly whether it's 1 or 0 on the white dot. So the goal test is dots all false, yeah, all 0. So it's a bit different in it depends on your problem. Yeah, depending on your problem, you will look at your search state to be quite going accordingly. Yeah. Yeah, so let's look at this. Let's discuss about this. The state space for this particular environment. So if you look at this particular environment, you'll notice that the Pac-Man can be in these positions. So they are 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5. So 30 cells, right? 6 times 5, 30 cells. And so the agent position, the position of your Pac-Man can be in any of these, the 30, and he's facing in 4 different ways, right? Because he can face north, south, east, west. So therefore, you can have 120 agent positions because 30 times 4. So the foot count is the dots, the ghost positions. So here you have the ghosts. So the ghosts, there are 2 of them, and it's moving vertically up and down. And it can, so you notice there are 6 also this way. And because there are 2 of them, so therefore 6 times 2 is 12. And the agent facing 4 ways. Yeah. So that is the whole world state. It can be in any of that state. So yeah. So in total, because all these are just agent positions, foot count, ghost positions, and all those things. So in total, how many world states can you be? Because when you are here, where the Pac-Man is, this ghost can move, right? So at this particular position, you will already have 12 times, right? And then each of these is also like 12 times. And then you have to consider the food as well. The food count, if the food can be yes or no. So 2. So, so basically you will have 120, the agent position just now, times the food count, they are 30. But you can have yes or no, right? So 2 to the power of 30 times the ghost position can have 12, right? So again, because of that yes or no just now, and times 4 because you will have this agent facing 4 ways. So but that is the whole states. But if you want to simply do the pathing, then it's just 120 states for the path, right? You want to do a pathing. So for example, you just want to move, so it can be 120. But if you and state for it for all dots is you have the 120 and also the foot count to be considered. Yeah, so you don't care about where the ghosts are, right? Because that's your goal. You just want to know whether you have eaten all the dots or not. Yeah, because the ghost is in another another section. So why would you want to consider the ghost? Yeah, yeah. So things like that. It really depends on what your problem is. Um, this is what would be your safe passage be if you need to eat all the dots while keeping the ghost scared of you, because if you were to eat the dots, then it will run away from you. But if you don't eat, if you don't have anything to eat, then it will go and scare you. So therefore the state would be, because even the ghost is moving, so that's like quite many that you need to consider as well, right? Okay, so what does the state space have to specify? So basically you would need to specify the agent position, the dot boolean, whether there is food or not. Yeah, power palette. Okay, obviously when you see the dots, there is a big one, there's a small one. The big one will be where the ghost will run away from you, but the small one, it's still going nearing you. So you will need to consider how many are there and how many time left. Maybe there is a time here. So these are some of the things that you would need to consider to be included in your state space. Wow, this is quite a lengthy lecture actually. Yeah, maybe do you want to have a little break or you want to carry on? You guys are still there? Sure whether you guys
Yeah, I think for me it's okay if you carry on.
carry on, huh? So yeah, I carry on, but I think I will not take too much until 6 lah, huh? I know some of you need to prepare for buka puasa. Okay. So before we can like how do we move from one state to another state? What is the rule to use? Things like that. Mm, the best way to look at it, you will perhaps want to visualize. Yeah, you will need to abstract the problem into something that is easier to code. So basically you need to like put it into a data type, right? Because you need to code for each of these state you are in. So you will need to represent the problem either in a state space graph or in trees. So usually we can have both. Yeah, you can have a state space graph and you can also have a search trees. Because it will be easier to then how to say, quote it and understand the movement of the searching algorithm. All right. So a state space graph is a mathematical representation of a search problem. So nodes are abstracted from the world configurations, and the arc represent your action results, or your represent the successor. So basically, when you take the action, what will it become? Yeah. So the goal test is a set of goal nodes. Okay, and usually you will have one goal nodes, or it can be more than that, depending. Yeah, but usually it's just one. So a state space can state space graph can look something like this. Okay, so you start off with the one here on the left, this position. So from that position, you can move either north or east. So you have here, and then from this, so if I were to look at the one that is moving north, then it can move again north, or it can go back down. Yeah, so it's here, and many more, right? So you can also go to the east. So it can be on the east. So it's another one. So this one is like putting out the nodes of which after you take into account the successor. Yeah. So you just connecting it according to the successor that you have taken. Yeah. So the arc here, the arrow here is saying that you have taken that successor. Yeah, which is move to the north for this one. All right. So this is a state space graph. So obviously that's the reason why I mentioned that you do not need to like draw the whole thing. Yeah. So as long as you have few, then it will give you some flavor of what the state space graph can look like. Yeah. Um. So in a state space graph, each state occurs only once. So you see the nodes, these are one state. Yeah, so it can be many state, right? Depending on, yeah, I already mentioned to you how many states they are in. So yeah, this one I already mentioned just now. We can rarely build this full graph in memory. It's too big, but it's a useful idea. Obviously, if you want to put everything, all the states it can have, then it will be too big a graph. This one is another example. Tiny state space graph for a tiny search problem. Well, it's not so tiny, yeah. So it can be something like this, but yes, still, even though it looks small, yeah, so a few states only, but still it looks so messy if it is in a graph. So you can actually, writing it down into a state space graph, it can be very messy because it really depending on what your which successor that you take, and it can go like everywhere. Yeah, so like what you saw just now. But in a search, in a tree, you can have something like this. You have at the top is your starting, okay, yeah, or the current position, if you may. Then you just create a branch downwards to indicate the possible successor, if it were to take its successor. So for this particular position that it has at the starting point, then it only have these two. Okay. Then from there, then you will do branching again. So from the one on the far left, you can have it going to the east again, and then go to the north. Yeah, so then it can also go down back again. Yeah, so it can have three positions, and same thing, three positions after that. Yeah, so search tree is where you put out the all the branches that you may take after your successor function, and then you can plan out using the search tree, right? So and you can use that to find out your outcome. So the start state is the root node, as I mentioned just now, and the children correspond to the successor. Nodes show states but correspond to plans that achieve those states. Yeah. So most problems we can never actually build the whole tree, obviously. Yeah. Similarly to the graph just now. And obviously, using trees is easier to basically develop your solutions. Yeah, with if you were to put it into a tree type. Yeah. So each node in the search tree is an entire path in the state graph. So you can actually have both. So you have a state space. So you have starting from S. So from S, going to the next, if you were to execute your successor function, then you can have your path to go to D or E or P. So hence, in your search tree, your the branch will go to three branch, D, E, P. So from the left, yeah, from the left, D, E, P. And then from D, it can go to B, C, and E. So hence, there are three branch there, B, C, and E. For E, E is going to H and R. So two branch only, H and R. So hence, this H and R. Yeah. So then you can develop your tree accordingly. Yeah, according to the graph. I mean, you can have them both. So we construct both on demand, and we construct as little as possible. So you can actually construct both of them, but there is no need to construct the whole thing in the world. Okay. So if we were to follow the one on the far left branch D, then if your goal is G, yeah, sorry, again, if your goal is G, then you will look at the children at the search tree at the bottom there. You find your G. Okay. So if you're moving from left to right, then you will meet up G using this branch, right? Following this branch on the left. And the path is shown in red. Okay. So S, D, E, R, F, G. So S, D, E, R, F, G. So it can be, so getting into this G is shown in here. How about this G here? The second G is S E R F G. Yeah, SERFG. So maybe this second G is more optimum. Yeah. If you are looking at if there's some length in the distance, then that could be your cost. So yeah. But how do if we were to move from left to right and follow going down there, then you will find this the first G first. But if you were to go across this way and then choose the one in the middle, then you will find the G, this one first. So it really depends on how you move, right? And how do we know where to move first? That's the question. So yeah. This one, state graph versus search tree. Consider this 4-state graph. How big is its search tree? Okay, so this one is a typical quiz question. Yeah. So how does the tree look like based on the 4-state graph? This 4-state graph. So you can quickly draw that. So from S, you will have 2 branch, A and B, right? And then from A, you have 2 branch B and G, right? And then from B, you have 2 branch A and G, right? So S, A, B, yeah, yeah. And from B, you have A, G again, yeah, and so on. So do you want to draw all that? There's no need, but of course, few will give you some idea, yeah. So lots of repeated structure in the search tree because of this looping. Yeah, because of this loop, hence you will like do it again, do it again, do it again. Yeah. So it's like infinite loop. So you can have a tree from your problem. You can create the tree according to your state space, and then look at the goal. Yeah, usually at the bottom there. Yeah, so for example, this Romania problem. So you start off from Arad. So Arad will go to Zerin, Sibiu, or Timisoara. Yeah, so Sibiu, Timisoara, and Zerin. Then from there, then you can have its cities, the next state. Yeah, so you expand out all potential plans. So basically, all the 3 nodes, and then you maintain a fringe of partial plans under consideration. So basically, fringe means is the one that you are considering. Yeah. So you start off with these 3. Then you will need to like decide which is your fringe. So if I were to say from the left, then this would be my fringe. Okay. And then from your fringe, again, depending on your searching algorithm, are you to expand this node? I mean, having the fringe for this node, or go to the next one, you know? So either going downwards, Arad, Pagaras, and so on, or you expand Timisoara. It depends on the algorithm. So basically, in a general tree search, algorithm, you will have your function, your tree search, where you have your problem and or your strategy, and it returns a solution. Okay. Failure means returns a solution or you fail. And so first thing what you have in the body of your function would be, of course, to initialize the nodes in your tree. Okay. And basically knowing what is your initial state. Then you go one by one. So if there are no candidates for expansion, because as I mentioned just now, you expand your fridge, right? There are no candidates for expansion, then return failure. If there is, then choose a leaf node for expansion according to strategy. So this strategy, what strategy we are using, yeah? So we'll talk about that later. If the node contains a goal state, then return because you have reached it. Okay, so then return the corresponding solution because when you already reach the state, your solution would be the path that you follow, right? Okay, each state that you have been. But if you have not reached the goal yet, then you expand the node and add the resulting nodes to the search tree because you need to return it back later on because you have already expanded that node, right? So basically, that's the important idea in moving in your tree. Yeah. First, you need to decide which fringe, and then you expand your fringe. Yeah. And then, then what to do next is depending on your strategy. So the main question would be which fringe nodes to explore. Yeah. So when we already, this is your fringe, then what to do next? Do we explore downwards or do we go to the other side? Yeah. So that depends on your strategy. Okay. So what's this? This is an example tree search. So we start off with S, and then we move. So from S, so you need to start from the initial. Okay, now I'm following the general algorithm just now, yeah? So from S, then you have to the fringe, yeah? So that is your state, your current state. Then you will have your fringe, yeah? So you have D, E, and P, yeah? So you have already moved away from your initial state. So that's why I cancel out S. Yeah. Then you can either go to SD, that's your path next, or SE or SP. Yeah. So this is which one do you need to explore? So if it is SD, then you explore or expand your D. Yeah. So with D, then you have your fringe. So you have from D, if you look at your graph, D goes to B, C, and E. Yeah. So since you decide on D, then you cancel SD in the path. Yeah. And then you have next would be if you were to expand D, then you have your path will be SDB or SDC or SDE, all this. Yeah. So if you choose SDE, okay, you expand E, then you means, so I cross out SDE means because I chose that. Then I expand it SDE, then you expand the SD the E, right? So you have SDEH or SDER. So if I were to choose that one, then I cross it out. Yeah, so which means that's the path that I take. And again, with R being expanded, then I have SDERF because only one node after R. Okay. Then when you reach F, F can be going to C or G. Yeah. So then you chose that because you expand F already. Then you have either SDERFC or SDERFG. Then between the two, which one has already reached the goal? So hence you chose the one has already goal. Yeah. So you're just following the algorithm just now. Yeah. So, but obviously you do not need to like go through all. Yeah. So it's really depending on the strategy that you have. So somehow the strategy here is taking all on the right, the far right. Yeah. But of course, checking, remember the algorithm, every time you check if the node contains a goal state. So once you expand, you following your strategy, then you need to check whether you have the goal state within the after you expanded. Okay. If not, then you expand that node. Okay, and then add the resulting node to the search tree. Okay. Yeah. So the question is, oh, sorry. So basically, here you reach the goal, and then it just show you where the path of reaching the goal. So the question would be, which strategy that you should, I mean, what strategy that you take? Yeah. So just now I simply say, okay, this one is just choosing on the right. Yeah. But they are actually, a proper strategy. Yeah. And one of it is the depth first search. Okay. So this depth first search is a type uninformed search algorithm. Yeah. So what does it do? Depth first search is basically expanding the deepest first. Yeah. So the strategy is expand a deepest node first. Okay, so that's the strategy. And the implementation is where the fringe is last in, first out kind of stack. Yeah, so you're putting it into a stack type, yeah, data type. All right. So like just now, we have the same state graph, and we have the tree. Okay, so we start off with the initial S, then you have the fringe on D. Yeah. Then you take on this side, yeah, on the left. Then you explore B, yeah, because you need to go expand the deepest first. So because and it is last in first out. So you take this first and then you expand accordingly downwards. Then obviously next one would be C, then you expand down. Then you go E, then you expand down. Okay, expand and expand, right? Then you still haven't reached the goal, then you do to the next one, and then finish that branch and move to the next one, and then downwards. C, and then A, then G. So you notice, then it's already reached the goal here, right? So this is depth first search. It will take long if the branch is heavy on that side. Yeah, too deep there, then you will have to be digging deeply down. Yeah. Yeah. So there are properties that you notice. You can see whether you can find a solution if one exists. Because like just now, yeah, as I mentioned, we have to go through one by one down there. And it will take time and computational power as well if your solution is far on the right. Yeah. They will like take time to reach there. And but however it is complete because well, it is complete if you can find the solution, if it exists. Yeah. So that is what complete means. Guaranteed to find a solution if one exists. Optimal, can it find the least cost path? That's the question. If optimality. Okay, this is the search algorithm properties. Yeah. So you will need to consider whether it's complete, meaning to say, can you find a solution? Optimal, can it guarantee, can the strategy guarantee a least cost path? Okay. And we are talking about time complexity as well, space complexity. These are all the properties that you may need to consider in choosing your strategy. Okay. This one is just a cartoon of a search tree in looking at these properties. Yeah, so this one is when you start off with a node at the root, then you have your branching. It depends on how many branch you have. So you'll need to consider the branching factor, because you need to these are because you have all these properties that you will need to consider, right? So if it is one node, and your branching will be depending on how many nodes after that in the fringe. Yeah. So if there are many tiers, downwards. Okay, so that would be your, depending on the tiers that you have, that can be your maximum depth. Okay, so if there are M tiers, then you would be looking at B to the power of M nodes. Okay, depending on how many nodes you start off with. Okay, so solution can be at various depths. Yeah, so it can be the pink one are the solutions. So it really depends where it is. So it depends on where the depths are. Number of nodes in the entire tree would be your space. Yeah. So if they are depending on your branches, then that would be the order of B to the M. That would be the total nodes you have, because it depends the states. Yeah. So if we have established that for a depth first search, then you are looking at moving downwards this way for depth first search. So it move it that way, and then it will reach the deepest solution. Yeah. Yeah. So as you can see, what nodes DFS expand, it expanded to the in that degree, right? B to the power of M, because it goes to the deepest tiers. Okay. And unfortunately, depending on where the goal is, it can actually process the whole three. So if M is finite, it takes about to the order of B to the power of M, as I mentioned just now. So how much space does the fringe take? It's a lot. Yeah, so has siblings to pass. So it depends on the branches, how many branches you have, right? For each siblings. Is it complete? If the M is infinite, then maybe not, right? So it can be complete if you prevent the cycle. So it meaning to say you have a finite depth. Is it optimal? Unfortunately not as well, because you will only find the leftmost solution. Okay, we don't know whether that is the optimal or not. Depends on the cost, right? Yeah. Yeah. Very quickly, perhaps. Where am I now? Still two more strategy to go. So I don't know whether you want to continue. It's already 5:30. If you guys are here, then I would carry on. But you're online, so it's, you know, the motivation to teach online is really low at this moment in time. Yeah. Shall I continue to cover breakfast search? Do you want to know? Okay, let me do breakfast search very quickly, yeah? And then after that, we'll stop. Okay, just to so that you can compare with depth first search. Yeah. So breakfast search, I think based on the name, you would know what it entails because you already know, you already understand depth search. Depth search goes deep down first. So obviously for breakfast search, it explore or it expand. Once it fringe out, it expand breathway, not depthway. Yeah. So it expand the shallowest node first, and when it creates the fringe, it will do a first in first out queue. So when you code this, you will be using queue. So let's do this. So you have the same example as just now. You start off with S and then you fringe out D, E, P. So where do you explore? So first is D, yeah. So then you fringe out B, C, E. Then do you go to B for breakfast search? No, you go to E. Okay, so that's the difference. So it goes to the shallowest first instead of for depth first search, it goes to the deepest one. So it fringe out E and then it fringe out P. Okay. And then, okay, so now that all the nodes are fringed out, then it will go to the next shallowest one, would be B, right? So fringe out B, then fringe out all that C, E, H, R, and so on. Yeah, so it goes to the right first. Yeah, so it goes like that. So, what nodes does the breakfast search expand? Because it goes to the first one, so it covers there, then it covers there, it covers there, and then covers there. So it really depends on which tier you are in. Yeah. So that's the nodes that it expand. So the process is that it processes all the nodes above shallowest solution. Okay, so if we take that to be the S tier, hence the nodes that is expanded would be of order B to the power of S, and how much space it takes. Again, roughly on the same thing because you are looking at that particular tier only. Okay, the last tier that you are looking at. So of order B to the power of S again. Is it complete? Because you're moving on the shallowest first, and S must be finite if the solution exists, right? So because this is so, then it is complete because you can find the solution. Is it optimal? Only if the costs are all one, then it will be optimal. But if it is as you move, the cost is different, then maybe not, right? Because the one that he found first, the BFS found first, could be costing more in comparison to the other solution. that is at the bottom. Yeah. So the difference between the two, DFS and BFS, is that obviously the strategy is distinctively different. Okay. When will BFS outperform DFS? Well, obviously, if the solution is, at the shallowest part, when will DFS outperform BFS? If the tier, if your problem has a shorter tier and the solution is on, on the left side, then obviously it will outperform BFS. Okay. So that's the two different strategies. This is uninformed, meaning to say you just move according to the strategy that we have. Here is a demo on BFS and DFS. Okay, so it is trying to find a path, the green one trying to find a path to the red one. Okay, that's the goal, yeah, for the green to move to red. And the dots is its nodes, yeah, the space, yeah. So the space that it moves according to the strategy. Okay. So what do you think this, what searching strategy did it use? Okay, you think about it. Let's see the other one. This is another one. So first one. And second one. First is what and second is what? Let's stop there. Very fast. Well done, Veronica. Hey, oh, okay. Someone else is already. Kevin is the first one. Yeah. Yes, the first is BFS. Second is DFS. Very good. Okay. I think I can stop there. It's quite tiring already, yeah. So those who have not taken your attendance, please scan now before it's 6 o'clock because it will stop at 6. So thank you so much. I really don't like to do online class because I couldn't get your feedback and I cannot see your face. But anyways, I really hope that you have some idea of what is searching algorithm. Well, basically tying the searching algorithm with coming up with AI. Yeah, so like I mentioned, it's a long story, just from last week. And a little bit of, before we move to searching just now, is on, we are talking about creating an intelligent agent. And so this intelligent agent should be acting rationally, yeah. And basically you are creating a problem solving agent, and hence any problem has a solution. So you are trying to find a solution, yeah. So you're searching the solution. So that's how it ties up, and that's why you are learning searching algorithm right now. And it really depends on the problem. How do you formulate a problem into a searching problem? Yeah, so I have already covered what are the things that you need to have in a searching algorithm, in a searching problem. Yeah. So when you're looking at the problem, you need to formulate the problem that it becomes a searching problem. So remember, for a problem to be a searching problem, you will need to have state space, uh, start space, goal space, successor function, how it moves, all these things. So all these, you will need to really formulate that, write that down. And if you are able to do that, then you can use all these searching algorithm that you are going to learn in today and also next week. Yeah. So these are yeah, basically what we are doing right now. Yeah. So more to come, more searching algorithms that we are going to look at. Okay. All right. So this Thursday you will have class with Sarah. Sarah and I want to check with you. Remember, for mathematical modeling course, I always have a buffer class. So if we are not mistaken, you are free Thursday 11 to 12, and also 2 to 3, right? Yes, everyone free Thursdays 11 to 12 and 2 to 3. Oh, I need to pull out the chat. Yes? No? Hello? Are you still there? Yes. One yes. Free. Okay. So can I have these 2 slots as our buffer? Therefore, in any case, we could have a very nice 4-hour class from 11 to 3. Yeah, if there is a need. Of course, we can have breaks in between. I just want to book that. I want to book that because, as you know, you will have your group presentation, blah, blah, blah. So I'll need to have buffer. And also many of um, our holidays, our public holidays, always happen on Monday, and the Monday class, it needs to be replaced. Some of it. Don't give me all these icons or emojis, you guys. Um, yeah. So please can keep those two two slots to be free. Okay, and yeah, we will have that as our buffer. So what happens next? This Thursday you have class. Next Monday, Hari Raya, right? Oh my God, it's Hari Raya already. Selamat Hari Raya, everyone. especially those who are celebrating. May you have a very grandest celebration with your family and friends. Yay! Yeah, so obviously our Monday class is not there. Then Thursday comes. Thursday, do you guys want to have class? It's gonna be online again. And we are still in right mood, right? Yeah, Isian, you're right. We don't want to have class. Okay, so um, I'll check. And we will let you know. Um, I think obviously on Thursday, we will not have synchronous class. But we are going to give you something to do. What high class can, God class cannot? Tak paham, Kevin. Okay. So what I'm saying is that Thursday next week we will not have synchronous class. However, I think I'm gonna do something for you to do, of which you know you'll need to do it to show that you are you know so-called attending it. All right. And then I'll see you the week after that, face to face, right? You are coming back already, right? 7th. Yes. Yes, thank God. So I will meet you guys face to face on the 7th of April. Right? Yay. Okay, so that's it for today. Selamat Hari Raya kepada semua, terutamanya kepada mereka yang celebrate Hari Raya bersama family dan kawan-kawan. Okay, itu saja. Terima kasih. Take care and have fun. Thank you. Don't forget to come to the class on Thursday. Nanti Sarah marah pula, ya? Okay, bye-bye. Thank you. See you soon.